So, we have read two very simple algebraic systems, and some examples also we have seen that how they are satisfying the property. Particularly we have used the closure, the associative and the identity element, and then how they are forming the semigroups and the monoid. Now, there are some variant or again some subset, because whatever algebraic system, mainly we have defined that it has a non-empty set and the operations are operating on this set. So, how they behave when we will consider a subset of the set. So, again algebraic system we will read, and mainly we will consider the subset of the set of the algebraic system, and then we will try to find some more properties. So, first, since now we know we have read the semigroup, and semigroup, now if I quickly summarize, it has the property of closure, and associative. Okay. And monoid, we have seen the closure, associative, and it has some identity element. Identity exists. I write identity element exists. Now, we define a subsemigroup, because for both these cases we have considered a set and we have given examples. So, now if how we define a subsemigroup. Or submonoid. So, first we define a subsemigroup. So, let S be the non-empty set and star is the operation. So, S star be a semigroup, and T is a subset of S. Then T is called a subsemigroup of S star if T is closed under the operation star. So, as the name is subsemigroup, only we are taking one subset of S, and the only condition is that this subset must be closed under the operation star. Now, similarly, if we define the submonoid, so again let S star E normally we write M by monoid, we give the notation M. Say M star E be the monoid under operations star. The operation star, and let T is a subset of M then T is closed under star and the identity element also exists. That means E belongs to T. Then we call that then is a submonoid of M star E. Okay. Now, we can take the example of that submonoid. We take that set of integers. Okay. We consider set of integers. Okay, set of we consider set of positive integers z plus and the operation is addition. Okay. Now, already we have seen that z plus under operation E and my identity element is additive identity is 0, this exists. So, this is a monoid. Now, let A be the set of odd integers, that means that is A is 1, 3, 5, 7 like that. Okay. So, A is a subset of Z plus, all set of odd positive integers. Okay, set of odd positive integers we have taken. Now, see, if we consider the set A, that is only odd integers, so it does not have any identity element. So, since it does not contain 0, so A of the subset A has or does not contain 0. So, there is no identity element. Again, it is also not closed. Again, A is also not closed under addition. Since if we add two odd numbers, then the result is even, and which is not an element of A. Since A is the set of odd integers. So, neither it satisfies the closure property, not even it has no identity. So, it does not satisfy the closure property or it does not have any identity also, additive identity. So, first thing, it is not a semigroup, subsemigroup, not A is not a subsemigroup. Not also not a submonoid, not a submonoid. Okay. Now, we have seen we have defined that monoid, that mainly it holds the property of closure, associative property, and it must have some identity element. Now, it holds some other property, like there are some variant of monoid we call, that is a cyclic monoid, and it is very important in some real algebraic systems. So, first we define what is we call that cyclic structure. So, if it is the cyclic property, we can tell see if we can it is a algebraic system, it has a set, and if there exists one element in the set such that the all other elements can be generated from by taking the power of that particular element, then it is called a cyclic in nature, and that particular element is called the generator of that system, the algebra. We tell that if say A, if we consider a set A, if we consider a set A and element and then element A belongs to A, then the all powers of A, if we take all the powers of A or A, then say A into A square, A cube, like that, that means say some A to the power n, A to the power m, and obviously operations I am taking as the multiplication, operation is multiplication. Now, if the set A contains all these elements, say A square, A cube, A4, some A to the power n, or A to the power n, then actually we using this A, taking the power, we can generate all other elements. So, in that case this has some cyclic property, have some cyclic property, and A is called the generator, is called the generator. Now, we define the cyclic monoid. Okay. So, we can define the cyclic monoid. So, I can write that a cyclic monoid, just now the way we have defined that algebraic system, only now algebraic system we are considering a monoid. So, it is M star E, in which every element of the set M can be expressed as some power of a particular element that belongs to M also. Obviously, particular element A belongs to M, then I can write that x, if x belongs to M, then x equal to some A to the power M. Okay. So, this is my definition of cyclic monoid, some power of particular element A such that if x belongs to M, then x equal to A to the power M, some power, and M belongs to some integer. Now, if x y two elements that are belongs to M. So, obviously, we can write that x equal to a to the power m and say y equal to a to the power n. Then I can write that x star y, that is a to the power m into a to the power n, is a to the power m plus n, is a to the power n into a to the power m. This is y star x. This star is the multiplication we are writing. So, that means it is commutative in nature. X star y, we get y star x. Okay. Is commutative. Now, we see this is cyclic monoid. Now, there are in real life there are many applications in real algebra that actually it satisfies this property of cyclic monoid. We see one of the examples that our modulo operation is very popular in many algebra, that and many application areas like coding theory, cryptography, and that is actually it satisfies or any system under this modulo operation, this becomes a algebraic systems like cyclic monoid. We take one example of that. So, we take one example. So, let S be an a set having 2-digit elements. That means 0 0, 0 1, 0 2 in this way up to 9 9. Although we write 0 0 is 0, 0 1 is 1, but just for symmetry we are writing this way. Okay. Now, the operation we consider is modulo 100. That means, what is this operation? The modulo 100 is if I take one element or some number, if I divide it by 100, we will be taking only the remainder. Since 100 is 3-digit number, the least 3-digit number. So, if I take the remainder can be only up to 999. That means it is closed. So, this is modulo operation. That means it takes that modulo 100 is the operation that if one number is divided by 100, it will give, we will consider the remainder, give the remainder of 2-digit numbers, of 2-digit numbers. That means again 0 0 0 to 999. So, now we have to check that So, we will check the first is if A star is abelian monoid. Okay. Here abelian monoid, abelian means it is commutative. Abelian monoid if it satisfy the commutative property. If it is commutative property it satisfy, then it is a abelian or commutative monoid. Commutative property. So, we have to check whether A star is an abelian monoid. Then find the identity element. And we see the cyclic monoid generated by determine the cyclic monoid generated by say some number, okay, 0.7. So, with this example, and obviously here with this example we see the some more properties of the monoid, and this star here we consider the star is the operation of means the modulo 100. Star is the operation of modulo 100 for this example. Okay. So, first we see what is the identity element. Better we see the B first. Since my set is S is zero zero 01 02 like 99 99 all 2-digit numbers, and my operation is star, which is we take that modulo 100. This multiplication and then we take the modulo 100. So, 0, okay. So, if I take the multiply with 0.1, that means if I take a 2-digit number, we multiply with 0.1 and divide it by 100, take the remainder, that means modulo 100 will be getting A only. Since A star 0.1 is A and that is and A belongs to S, that means A is a 2-digit number. So, 0.1 is my identity. This is my identity element. Now, if we call, so this is actually my B, answer of B. Now, we check whether it is the first question was what is abelian monoid, that means whether it is a commutative or not. So, first thing is it will be closed, it has some identity. We have to see whether it is associative or not. It has identity, since hundred is least 3-digit numbers. So, always the remainder, that means some number modulo 10, I take the n modulo 100, n modulo 100 is 00 to 99. So, it is closed. Then whether it is associative or not, it is closed. We check the associative property. So, if we consider 3 elements A, B, C of 2-digit numbers belongs to S. Now, since it is closed, so if I consider say first A star, B star, C modulo 100, and then again this is modulo 100. That means I am taking, first I am considering, I am multiplying B and C, and all my A, B, C are 2-digit numbers. So, since it is closed, so B star C modulo 100, again it will be giving another 2-digit number, say D. So, let B star C modulo 100 is D. Obviously, D belongs to S because it is closed. So, this becomes now A star D modulo 100, and say B star C modulo D, and let the A star D modulo 100 is E. So, say my result is E. Here all that E is also belongs to S. Now, we see that since it is associative property, so first I do the A star B modulo 100 and star C modulo 100. Now, since we are getting this A star B modulo 100, we are taking the last 2-digit numbers, only the remainder, and again that is multiplying with C, we are getting taking the remainder when divided by 100, obviously we will be getting, and again remainder means last 2-digit numbers, it will be E only. We take some examples, that say I get A is 05, I take B is 89, and we see we check. Then if I multiply A star B, okay, I should take another value, say C equal to 08. So, if I take say A star B star C and this modulo 100 is there always. So, then it is I get 5 and if I multiply these 8 and 89, this will be getting only 12 because divided by 100 modulo, that means remainder will be 12. So, this is 12. Now, if I take this modulo 100, it will be only 60. Now, if I do the other way, that A star B modulo 100 star C modulo 100, then I will get A star B is 5 and 89. So, that will be 445, remainder is 45 only, 45 and here it is 6 because my sorry C is 8, C is 8. So, if I take modulo 100, so 8 into 45, this is 36. So, I will be getting only the 2 digits. So, this is also, if I divide by 100, it will be giving me the 60. So, I see that it is also 60, it is also 60, that means associative property holds. So, what I get? That first thing is that for my A part, that I see that the system defined here is closure, property it holds associative, it has already we have seen identity 0 1, identity exists. So, it is a monoid. Now, here we see that if A star B modulo 100 obviously is B star A modulo 100. So, it is commutative, that means it is abelian, commutative or abelian. So, it is abelian monoid. Now, C part, it is generated by, generator is 07, generator given is, generator is 07. So, if I 07 modulo 100, since it is only 2 digits, so I will get 49. So, if it is 49 star 07, that means it is 07 square, if I write in this way. Then again, if it is 07 cube, I get the 49 into 07 modulo 10, sorry modulo 100 we are taking 2 digit numbers. So, it will be, we will get, it is 43. Now, again if I get 07s, okay, I write here 49 means actually this is 07, I can write the same thing as the, it is as 07 star 07 star 07, I am taking power 3 modulo 100. Now, in this, now if it is already 43, so if I write 07 star 07 star 07. So, actually this will be, this is modulo 100 is actually 43 star 07 modulo 100, and this becomes 01, because if I multiply, so 301, so divided by 100 means it will give you 01. So, now again if I multiply 07 star 07, another power, if I increase, either it was 4, I will be getting, since now I got the identity element 01. So, obviously I will be getting 01 into 07. So, since already I got, so it is 07. So, it is cyclic in nature. So, what I got, first the generator is 07, the second it is generating 49, then 43, then again 01, and now it will repeat. So, the cyclic monoid we get, right, the C part, the cyclic monoid generated by 07 is, I should write 07, then 49, then 43, then 01. And it will repeat. Okay. So, we read monoid, and then there are some other properties that one monoid can hold, and these type of we can see and we can check that there are the general properties that we read, that again some algebraic system how they hold. Like we have just now we have seen the abelian monoid, that means it satisfies the commutativity. Similarly, it can be abelian semigroup. So, if the semigroup satisfies the commutative property, it will be the abelian thing. So, next lecture we will identify some more algebraic systems or the larger algebraic systems and how they satisfy the properties.